start today with a little theoretical explanation of what we do, and then I will jump into the Python programming. Basically, I am going to explain today how to analyze I'm going to try to explain how to analyze three or more dimensional data sets. Imagine an example. You have on one column the different products, product 1, product 2, product 3, 4, 5, 6 of a store, okay? Let's say 1 are shoes, and 2 are trousers, and then you have shirts and so on. Okay? And here you have the time when people purchase, okay? 8 a.m., 9, 10, 11, 12. So, and then you go and say, well, at 10, between 8 and 9, people spend 35 euros on shoes, on the category 1, and here only 10, and here 68, and stuff like that, okay? So 71, and 82, and then on the category 2, you have 17, and 8, and 27, and then 160, and 13, and so on. Okay? So now imagine the more money people spend, the darker it gets. So we color each cell and if people spend only 10, well, it's only one, it's very clear blue, but if they spend 160, it's very dark blue. Okay. And we paint these pixels or these cells darker the more money people spend. This is a typical three-dimensional problem. You have one dimension, which is the products, 2 dimensions, which is the time, and the third dimension is given by the pixels. Okay, the amount of blue that the pixels are, or half. Okay, this can be coded. It's the same problem as analyzing a picture. So if you have pictures with pixels, and I guess you know what pixels are, and some pixels are dark, some pixels are not so dark, and in the end they give an image. Okay, so you get say a number 1. So if you have a picture of the number 1, okay, the pixels that are representing the number are going to be blue, and the rest are going to be white. So the problem that we solve now is the recognition of patterns through machine learning in multi-dimensional problems through dimensionality reduction. Why dimensionality reduction? Because as you see, this here is a three-dimensional problem, but we represent it in 2 dimensions. Only 1 and 2. Okay. We're gonna learn how to recognize patterns of customers, for instance, by recognizing, by bringing a multidimensional space into lower dimensions. And we're going to use 2 methods, one called principal component analysis and one called TSME. Okay. Do you have questions? About the problem framing? No? Okay. So now we start by defining the problem. Okay, we start now with a PCA, okay, called, as I said, principal component analysis. Okay, this is eine unsupervised method, so people don't need to do anything or know nothing about the data set. The first thing we do is we get NumPy as NP, then we get matplotlib.pyplot as PLT, and then we import Seaborn as SNS. And we get our sets. So this is just importing. If you don't have all these libraries installed, it's easy. Just say pip install NumPy or pip install matplotlib or pip install Seaborn. Okay, you just write that, you will get the libraries. So the first is we upload a 2-dimensional data set. We start with 2 dimensions because it's the easiest. Okay, and this is going to be called RNG. Some random numbers from NumPy, random state 1, and X is going to be our data set, and P dot RNG random 2 by 2, RNG random 2 and give me 200 data sets. True, and then just plot me the data in a scatter plot with the first column, 0, and the second column of the data set. BLT axis equal. State is big. State is big. Positional argument. So here is our data set. Okay. And this is just some random numbers from in a range from -2 to 2 with a standard deviation specific to 100 data sets, so no problem. Now we are gonna perform the PCA calculation, and then from sklearn, the composition, import PCA, and then PCA is just equal to PCA in 2 components. PCA bit X. So this is done. I just need to print it. PCA components underscore, and these are the PCAs. So I draw a vector. This is not this line is not relevant for exam. Okay, so what I wrote in this line, this specific line is not relevant for the exam. Just this is just to explain what the PCA does. Okay. It is annotate. I just have prepared it before, but it's not going to be relevant. Okay, so what does the PCA? As you see here, this cloud of points, this blue cloud of points, is better explained by the white arrows. Okay, so I have one principal component, which is the first long arrow, and I have a second principal component that is the perpendicular, which is shorter because it explains less variability of the data sets. The arrows explain better the information presented in the dots as the X and Y original axis. So what we do with the PCA, with the principal component, is we just find a data set that is or we find 2 directions that explain the data set better than the original axis. Okay? Questions? Hello? Any questions? No? Well, then this is just for 2 dimensions. Now imagine we try to do the same for more than 1 dimension. Okay, and this is where it gets tricky. And this is the area where you're going to be moving when you work later on. Okay, so your boss is going to ask you to give him a recommendation of what are the most important aspects or KPIs or suppliers in a certain data set. And it's going to be a huge Excel table with hundreds of lines. Okay, so with 3 or 4 lines of code that you're going to learn today, you can tell him, well, the most important aspects of this process are this, this, and this. Okay. I'm going to use a data set for breast cancer, but you can do you can name the columns as you wish. Okay. Import pandas as PD, then import numpy as np, and import matplotlib.pyplot as plt, and import seaborn as sns. Okay. In the exam, please make sure that you write all of this down, because otherwise it will not compile. Okay, so from sklearn datasets, some of you have asked me, where do I get data for my bachelor study or for my bachelor arbeit, where you can get data from sklearn. There are millions of data sets that you can just use, and they are in Python. Okay, so if you called cancer equals load breast cancer, and then you say df, the data frame is pd data frame cancer data, and the columns are equal cancer feature names, and then you press shift enter, and then you say df head. What you get is a data set of 30 columns. 30 different KPIs explaining the behavior or the breast cancer state of many patients. I have as much as 570 patients with each 30 different data sets. Okay, 30 different KPIs explaining their cancer state. And of course, I know if these people died or if these people got cured, so I can sort of later on create predictors that say what is the life expectancy of a patient that has a certain set of KPIs. If the mean radius is bigger than this and that, or the texture, or the perimeter, or the area, or the smoothness, and so on and so forth. Okay. So as you can see, the first thing we can see is that these data are moving in different dimensions. So here, for instance, you see the mean perimeter is moving in the range of hundreds. The mean texture is moving in the range of dozens, but the mean compactness is never bigger than 1. Okay, so as the worst perimeter is around 150. The worst radius is around 20, and so on and so forth. So to compare this data without doing anything is very dangerous. Okay, that's why the first thing you need to scale the data set before processing, and this is super important. Okay, one way to do it, and a very effective way to do it, is to use sklearn pre-processing, import standard scalar, sorry. Okay, and then we say scalar equals standard scalar. So we put it in the same. So now our standard scalar is going to fit our data set just by writing scalar.fit of df, and then we say scaled data equals the scalar transform of df okay. Second, this type here. So scalar fit. Scalar. And then if I right now scaled data and press Shift Enter, I get an array that is already scaled. Okay, so this is just the same data set as before, but it's scaled around 0. Okay, so it's normed around 0. This is one thing we did 2 semesters ago when we performed the same calculations by hand. But now we can do it with the computer. Okay. Still, we have 30 dimensions, and this is impossible to chew if you have a computer, if you have only paper, or if you have Excel. It's impossible. Okay, so we want the computer to tell us the 2 main components of this. What are the main drivers for people to die of breast cancer? What are the 2 main KPIs explaining the variability of this data set? Okay. So the question is, what are the main drivers of variability in the data set? And this is what PCA is going to be explaining. So with 4 lines of code, we can perform our PCA. With 2 PCA components, we can do it with more, but it is enough. So we say PCA equals PCA of n components equals 2. Then say PCA fit. the scale data, and then you say x PCA equals PCA transform. And this is important, we perform the PCA on the scale data, not on the original, but on the scale data. Okay? And then we say x PCA shape. Okay? And he's going to, if everything went well, yeah, we have still our 569 data sets, but now they are projected on 2 dimensions only. Okay? So now we have 2 dimensions only, as we wanted, because we have 2 components. If we have put here 3 components, then we would have 3 components. Now, if I plot the figure, if I plot the new data set, graphic representation of the data set, 30 dimensions are projected to 2 dimensions given by the PCAs. Okay. So in order to do that, we reserve some memory for the figure. Fixed size equals 8.6. This is just the figure size, and then we just say plot scatter x PCA, comma 0, then x PCA, double bond, comma 1. C is cancer target, and CMAP equals plasma, just so that it's pretty, okay? And then PLT X label is first principal component, and PLT Y label is second principal component. Shift enter. So you get the information that we had before in 30 dimensions is now represented in only 2. The first principal component in the horizontal explains more variability than the second principal component, and the data set is divided into 2 clouds of points depending on the target measure. We can also represent this numerically if we say, well, this is the principal components. And the first vector is this one. This is the first principal component. And the second vector is this one. This is the second principal component. We can also represent the variability explained in a heat map. This means how much variability is explained of each variable by each PC, by each principal component. So in order to do so, we define from the data frame the components PD data frame PCA components. We have them from up. The columns are those of the original data set, feature names. Okay, this is the original information. And then we say PLT figure fixed size equals 14,6, just size, and then give me a heat map of the data frame component. So, and here you can see the original datas, okay, the original KPIs, and this is what you would show to your boss in the company, okay. So we can see here that the mean radius of the breast cancer, you can see that the first KPI here is the 0, okay, explains a certain amount of variability, which is the amount of red or rosa here. So it's around 0.25, let's say. And the second KPI explains nothing of this. So the clearer it gets, let's say mean fractal dimension, the more information it's being explained by this data set, by the KPI. So each one of the lines here, so 0 is the first PCA and 1 is the second PCA. You can see how much variability is being explained by each principal component from each KPI. Okay? Questions, please. Okay, well then we'll make a little break. We'll make a little break and we continue in another 10 minutes. Send you another invitation. Bye. Start again with or we continue with the TSNE. Okay, this is called the T-distributed stochastic neighbor embedding. This is a methodology that is not supervised. It's a nonlinear technique that explores data sets and enables a visualization of multi-dimensional data. Okay. The difference with PCA is that PCA is a linear dimensional reduction method. PCA tries to reduce the variance to maximize the variance by keeping the distance between the data, and TSNE is a non-linear method, so it can explain more things than PCA. That only keeps distance between data or local similarities. Okay. So how does it work? The algorithms calculates the distance between data in the high dimensional space and projects this into the lower dimensional state. So let's say 2 dimensions in order to visualize it. And tries to keep the relative distances by optimizing a cost function. Okay. So the first step, step 1, is to measure the similarities between the points in the high dimensional state. In order to do so, we I'm going to import a picture I have downloaded. My figure, let's go. Zero one tip. Let's get the image format. I wanted to introduce some figures, but so let me just open it and share it with you like this in the video. Preview. So here you see the picture in the middle. So this is a Gaussian distribution around the point. So we look at each point and have a Gaussian distribution around the point. So a normal distribution. What is a Gaussian distribution? A Gaussian distribution is a Gaussian distribution. It's something like, as you know, like this. Okay. Second figure. Okay. This is a Gaussian distribution. So it's different. The Gaussian distribution is a gray one. It's different than the Cauchy distribution, which is more steep. So we try to find a Gaussian distribution of points around the each point of the data set. Okay. This means that the second step
is to find similarities between the points by implementing a t-student or Cauchy distribution. And the reason is that the Cauchy or t-student distribution has only one liberty degree. The normal distribution has two. So the step number 3 is to calculate the distances between the points of the high dimensional space and project them into the lower dimensional state. And for instance, we can try this easy. So import matplotlib.pyplot as PLT, import seaborn as SNS, sns.set, and import numpy as np, as we have done already before. And now we're going to load some digits, some images, as we saw before, sklearn.datasets, import load digits, load digits, digits.data.shape, sklearn. Datasets. Digits is not defined. So this is very normal. When you type, you mistype yourself. So it's no problem. So now we get a multi-dimensional data set of 1,700 different digits. Each one is 8 by 8 pixels, so 64. Okay. This function that I write now, this is not relevant for the exam. Okay, this lines of code. Okay. Only this, not the next ones, but this is. I'm just trying to plot the figure. So it's just. Similar as before, so not. Well, no, it should be relevant for the exam. It's not nothing new. You should know. So once I do that, it takes a little bit, and it represents some of my data. Not all the data, but some of my data. Okay. So you can see I get. This is as we saw before, as we saw in the introductory
notes that we took today. This is just a 3-dimensional data set represented in just 2 dimensions. So we have a y-axis with the different numbers, the positioning of each pixel, and then on each pixel I have information. Okay. And the key is here: can we teach our system to recognize the numbers? Okay. So can I recognize if it's a 0, a 1, and 2, and 3, and 4, and then represent all this information that is in the multi-dimensional data set, represent all this information into a 2-dimensional graphic that I can show to my boss. Okay. And it's kind of interesting because what we then get is something that any manager can understand. So digits, targets, target. So we have different numbers. Okay, 1, 2, 3, 4, 5, 6, 9, 8, and so on and so forth. And what we try to do is we get the first 600 of this data and called it X, okay, and the target numbers of this data and called that Y. Okay. So here in X, in data X, we have the pixels, and on data Y, we have the labels 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we perform the TSNA from sklearn.manifold, import TSNE, shift enter. Okay, so we have imported it. And then we say TSNE equals TSNE big, 2 components, 2 dimensions, comma, random state equals 0. Shift enter. And then we say TSNE object equals TSNE dot fit underscore transform data X big TSNE dot object. Now it thinks a little bit, and now we have transformed the data into a 2-dimensional array. Okay. Now we can add one new column, which is giving me the information for each point on this XY axis, what type of digit it is, so what target we're talking about. Import pandas as PD, and then we say TSNE df data frame equals PD.dataFrame, and X TSNE underscore object, comma 0, then comma Y TSNE underscore object, point, comma E, 1, comma, and then digit. I add another column called digit with the labels. Then I say TSNE
underscore df.head. And if I haven't misspelled it, all the data which are points in a two-dimensional frame are represented and are labeled with 0, 1, 2, 3, 4, blah, blah, blah. So now I can just scatter plot it as an instance scatter plot x minus x, comma, y minus y big, and data equals DSNE underscore df.
So now you see what this is all about. Each of these groups is going to be one of the numbers. 0, 1, 2, 3. These points that are really not grouped together, the algorithm is not understanding very well. But you can see this group here by x30 and 40 and y minus 20 minus 30. This group is very well defined. This is going to be one number, I don't know, number 7, okay? And we have represented this information. We can do it a little bit more pretty if we want. I prepared it before. So each number is one color. You see? Each one of the numbers that we had before in a certain code, okay, in a certain pixel code that was not understandable for us, is now represented in a way that any manager can understand. Because now we can see we have different types of numbers and they are color-coded in a two-dimensional data set. The same thing, the very same thing you can do if you perform this analysis with different suppliers and you have multi-dimensional data set or Excel table. You can do the same and try to represent that for your boss and say, well, here you see all this information. You can cluster your suppliers into 10 categories or into 5 categories. And this is clustered and this is represented as this image. Okay, so with one single figure, you can represent hundreds, millions of data sets. You have any question? Well, then we make a pause now, and I send you another invitation in a couple of minutes. Go get a coffee. We continue now with our last method today, which is called multi-dimensional scaling, or short MDS. Well, we will see one more example. So this is just our last method, and then we will see another example of PCA, which I think is interesting. We are going to learn how to scale information and code information in two-dimensional space. Okay, but in order to do so, we are going to generate multi-dimensional information. For that, we want to import matplotlib pyplot as plt as usual, import seaborn as sns.set, and import numpy as np. So in order to generate the information, this is not relevant for the exam. Okay, this line. I have prepared some code that generates information. Size. It's a function that makes some code, some data set in 3 dimensions. It just writes the word Prof H4 in 3 dimensions with colors. Invalid syntax. Okay, so I am going to this function you need to learn. I am going to plot just 1,000 points. Let's say I want 42. Okay, so let me try some more points so that you see that at the end we want to see something written like Prof H4. Okay. I'm going to use 10,000 points. 10,000 points. You can see we are writing 10,000 points that are explaining the words Prof H4. Okay. We can also take another name. Let's take Irena. Make Irena, and then I can tell him to write here Irena. Okay. So I say make Irena, and it writes Irena with a little bit of imagination. Okay. So this is just some data set which is multidimensional, because I have one x-axis, one y-axis, and then I have the points, and each point has colors. Okay. So I have 3 dimensions. The thing is that I can create a distance matrix of these colors, of these points. And by creating a distance matrix, I can recode this information in only 2 dimensions. Okay, and this is what our system is going to do. We are going to create a 2-dimensional data set, sklearn dot metrics. So the word IRENA is going to be transformed into 2 dimensions, pairwise distances of x big d dot shape 467 times 467. Okay. So now I can go and I can say, please plot me this information, okay, the interpolation, and this data set that we are seeing now, this matrix, has exactly the same information as the one before. It's just we cannot read it, but the computer has transformed all the distances between all the points, which are 467, into a new way, okay, into a distance matrix. And now it comes with our IMD, what's called MDS. Now we want our data set back from the distance matrix. We want back to our name IRENA, to our original multi-dimensional data. So how do we do it? Okay. How do we create from distance matrix? How do we go back to the higher dimension? This is not trivial, okay? And we will have to pay a price to go down into the 2 dimensions and then go up again. Just like when you project a shadow on the floor, you can get different forms, different shapes, giving the same shadow. Okay. So what we are going to pay is that the text can be rotated. The text can be rotated and still preserving the distances. MDS M components equals to this similarity equals pre-computed random state equals 1. This is our model, and the output is a model dot fit transform. This is equal of D, and then we just plot the scatter plot. We wait a little bit, and you see we have the word IRENA rotated. The reason is that we are uploading the data from 2 dimensions of the distance matrix again into a 3-dimensional or more dimensional state, which is and for this reason we create a rotated image and not the original. Okay. Questions, please? So thank you, Irena, for playing with us. So here now we are going to use a final example of face recognition using PCA. Okay, face recognition is something that, for instance, your iPhone does without any problem, and this is the algorithm that is being used. So a face, a picture is just a data set, which if it is black and white is 3-dimensional. Fetch people. Okay, we're just getting the data from sklearn, and we get 2,370 pictures of leaders of the world, and our data set has 2,914 dimensions. We can plot the data, plot some data by doing this. It takes a little bit. And you see we get George Bush and Ariel Sharon and Colin Powell and some guys from the Middle East and so on. Okay, some leaders in the world. And now we are going to try to represent. We're going to organize these faces in groups, okay, as if they were represented on sort of a blackboard, and all the pictures of Bush would be together, and all the pictures of Colin Powell would be together, and all the pictures of Ariel Sharon would be together, and stuff like that, okay? So in order to do that, we are going to use PCA, okay, a randomized PCA, to create clusters, and these clusters are going to be then represented with an isomap. So first we perform a PCA. And this is just, as I said, an example, an application, a real-life application of what this stuff can do. So the components, the PCA components are 100, okay, and we see that 20 of our PCAs can explain around 75% of the variance. Okay, so this is just a Pareto, and now we create an isomap. As I said, this is just in order to represent so the shape of a, well, he's creating the isomap, and the shape is going to be a 2-dimensional. So he's going to put all the pictures in groups following the fitting algorithm. And the projection is going to be 2-dimensional. So we're going to have 2,370 figures in just 2 dimensions. Yeah, so it's ready. So 2,370 figures in 2 dimensions. And now we're going to represent this into a 2-dimensional space. This is something you can do, for instance, when you work for the police. I have done it in the past. Import of setbox when you are studying a number of suspects. You can teach the computer to represent the data like this, okay? Or when you are representing a certain set of, I have prepared the functions before. Back. Yeah. Continue. Show offset and then here. So if I have not mistyped it, now we have our data set. We have a function that plots the components. You can, of course, use this function later on for your purposes. And then we just plot the images. It takes a little bit. Takes a little bit. The same you can do if you have pictures of your products, okay, and you want to visualize depending on the visual information of one product. Let's say all red T-shirts. You can teach your computer to put all the red T-shirts in one category, okay, and visualize them. This is something that, for instance, Amazon does. Well, not with PCA, Amazon does it now with deep learning, but you see what is the result. Okay, it's not perfect because we are explaining only one part of the variability. But as you see, let's say all the pictures or many pictures of George Bush are all together, or Tony Blair and Colin Powell is together and stuff like that. Okay, so you create different groups of figures that have same statistical information or similar statistical information. Okay, now imagine instead of putting these faces of ugly people, you put products. Okay, and you use this algorithm for teaching your computer, your system, or your company to choose between different strategies depending on the product visual information. Let's say all the blue trousers, or all the red T-shirts, or all the red shoes, or all the whatever. Okay. So, any questions? Okay, by this point, you should be having a lot of questions. Maybe you're not asking because you don't understand shit, or maybe you're not asking because you don't dare. So I am going to let you think about all this material of today and try to get some data set that we have mined in the past and try to implement PCA. So I'm going to give you one exercise. Mine data from Yahoo and perform TSNE PCA on it. Next week, we discuss your results. So next week you will be presenting your results. You need to mine data from Yahoo, multidimensional data from some Apple or some company, and then I want you to implement TSNA and PCA, and you are going to be presenting your results. Okay? Is that understood? This is an exercise, so please make sure, if you have questions, you can contact me anytime. I will upload, as usual, all the video on profh4.com. You can contact me via the YouTube channel by writing your questions, or you can contact me through WhatsApp, or if you want to call me, you can call me or write me an email, whatever. Okay? Well then, I hope I'm getting through. I am looking forward to getting your exercises. Enjoy, and see you or hear you next week. Bye-bye.